Okay, Algebra 2, let's dive into section 7.4, which is dealing with properties of logarithms. And these are some skills here that we're really going to need to pave the way for section 7.5, which is the big one we've been working towards, which is how to solve exponential equations using logarithms. So that's the end goal, but for right now, we've got to pick up some skills on the way there. So the first property we're going to talk about, there are four of them we're going to do today. The first one right here is called the product property for logarithms. And that one's written in the box right here. And I probably should have put parentheses right here. If you're taking a logarithm of a certain base, so we're just calling this log base A generically, of a product here that is a product, B times C, so the product of two different things, two numbers, being multiplied together. That big fancy logarithm can be broken down now into the log base A of B. Notice it's the same base of the logarithm, and B is the first factor in that product right there, plus, not times, which is what a lot of people want to say here, but plus the log base A of C, where C is the second factor in that original product. So one thing I want you guys to notice right here, the log base never changes. It's going to be log base A throughout this entire thing. But if the product here is a product, B times C, you can make it the log base A of B and the log base A of C, but you've got to add those two together there, not multiply them. So that's the property right here. I think rather than trying to tell you guys where that property comes from, I just want to dive in and do our first example here together, and I think this is going to explain, or at least we can kind of come back after the fact and verify that this formula is in fact correct. Now, I do want to point out something, guys, that I'm sure you probably know, so I apologize if I'm insulting you right here, that an equals sign, everybody, is bidirectional. You can actually read it in either direction. So the order in which we wrote this property makes it look like you would start with a single logarithm like this, and you could break it up then into the sum of two different logarithms. But of course, it also works the other direction as well. You can start with an expression that is the sum of two logarithms if they have the same base, and you can then land here writing them as a single logarithm. And that's what we'd be doing here in example A. We've got the log base 2 of 8 plus the log base 2 of 16. So if I read that property again, it tells me that if two logarithms have the same base, and these ones both have a base of 2, and they're being added together, we can write this now as a logarithm of the same base, log base 2, and then we can multiply these two products here together. So that becomes an 8 times a 16. Now, why would we want to do it? Well, that way, in this problem, it's not entirely clear why, and I'll show you in just a second. But if we wanted to simplify this on the right, this becomes the log base 2, and 8 times 16, feel free to use your calculator here, guys, is 128. And now, take a look at the question we're being asked. Log base 2 of 128 means 2 raised to what power is equal to 128? And the answer to that is 7. So that's the answer that we came up with. But as I said, I wanted to start you off with a relatively easy problem just to show you that this property works. And I don't know if anybody noticed this, but log base 2 of 8 is one we can evaluate right away. 2 raised to what power is equal to 8? That's 3. 2 cubed is 8. And then plus 2 raised to what power now is equal to 16? That's a 4. And sure enough, 3 plus 4 gets us 7 for our answer here. So we could really arrive at that answer of 7 two different ways. The first way that I did it in purple is using the property that we just learned. But every good mathematician should be a little bit skeptical of any new formula that they learn, and they should be saying, prove it to me that it actually works. So we did it a second way in red there that required not new information from 7.4, but stuff that we learned back in 7.3. Now that one, I shouldn't have used the P word. That one example is not a proof, everybody, but it does kind of give you a shove in the right direction that this formula here seems to work, at least in that one case. Now let's take a look at a second example. And I like this problem because you can't do this problem the way that we did this one here in red. Log base 3 of 54 means 3 raised to what power is equal to 54. Well, if you were to look at your power tables, guys, here's what you would learn. 3 to the third power is 27. That's too small. But 3 to the 4th power jumps up all the way to 81, and that's too big. So 54 is not a power of 3. So there is an answer to the log base 3 of 54, but it's irrational. And the fact that it's irrational means that we can't do it by hand, we can't get it from our table. So either we would have to use our calculator, which we're trying to avoid here, guys, and we're going to try to work around that, or we've got to use this new property that we just talked about. So two different logarithms, but they're written in the same base, and they're being added together. We can combine that now into one single logarithm, log base 3, and now we multiply 54 times 1/2. Okay, and that expression right there can be simplified. So this is now the log base 3 of, and 54 times 1/2, or half of 54, is 27. Oh, and by dumb luck, the log base 3 of 27 is rational. 3 raised to what power is equal to 27? The answer to that is 3. So that's what we come up with for an example there, for an answer for example B. Okay. So that's something that you can do with this property right here. Another thing, though, this is kind of an interesting one, is you can take something that looks really, really scary, like the log base 2 of a big number like 4096, and we might be able to break this one down and do just a little bit with it if we were just a little bit crafty about that. What do I mean? Okay, the question we're being asked right here is 2 raised to what power is equal to 4096? Now, most of us don't know the answer to that question off the top of our heads. And even if we were using our power table here, I don't believe that power table goes up this high in the row of 2 here. I think it only goes up to 2 to the 5th in most cases, which would only be 32. But what we might be able to do is get lucky. And we might be able to say, okay, is 4096 evenly divisible by any of those numbers that we came up with right there in that table? Okay, so for example, what if, okay, come on, here we go. All right, what if we took 4096 and tried to divide it by 32? So 4096, sorry, I'm typing this into my calculator here, guys, divided by 32 works out nicely to 128. So maybe I can apply this property from the first slide, oops, it disappeared, this property here in the order that it was originally written, going from here, one big logarithm, into the sum of two smaller logarithms. So let's see what we can maybe do here, guys. Maybe we could make this, I'm going to start a new line right here, the log base 2 of 32, and add to that the log base 2 of this number here, which was 128. This works, everybody, because the product of 32 times 128, I don't want you guys to think I'm lying to you here, 32 times 128 equals that big initial product that we had of 4096. Now, how is that helpful? I think that both of those two logarithms right there we can evaluate, hopefully by hand, maybe with a little bit of thinking here, but let's take a look. Log base 2 of 32 means 2 to what power is 32? That's going to be a 5. And then the log base 2 of 128. Let me think real quick, guys, off to the side. We just established that 2 to the 5th is 32. If I multiply by 2 one more time, 2 to the 6th is 64, and one more factor of 2, 2 to the 7th, gets us 128. So this becomes a 5 plus 7, and our answer there is 12. Now, what have we actually learned? That the log base 2 of 4096, I believe, is equal to 12. And I could check that now by saying, okay, 2 to the 12th power should equal 4096. Let's try that, guys. 2 raised to the 12th power, sure enough, is 4096. Now, I do have to be honest with you guys. The fact that your calculators nowadays are a lot more advanced than they used to be even 10 years ago kind of makes this a little bit of a moot point. For you guys on your TI-84, if you hit alpha and then F2, that gets you to a menu here, and if you were to then hit 5, you get something called log base. For me on this calculator, if I just push this log button right here, it opens up the same thing you guys just saw. So I hate to ruin all the fun, but we could just type in log base 2 of that big number there, which was 4,096, and it should give us the answer directly, which is 12. So the purpose of this section is partly to show you how we used to do it back in the day, but also, guys, a question like this could show up on a non-calculator portion of a quiz or a test, and you guys could handle it this way. So just wanted you to have that little trick there in your back pocket. So there's 3 quick examples for how to use the product property for logarithms. Now, we're going to move on to the second property, and you could probably guess that if there is a product property, there's probably going to be a quotient property. And if the product property involves addition, well, I think you know where we're going with this. The quotient product is probably going to involve subtraction. And here we go, guys. This is property number 2 here, and it works pretty much the same way. If you're taking a logarithm of any base, we'll just call it log base a, and if the number, this is really confusing because this number is the product of a logarithm, but if that product is a quotient, b divided by c, you can break that up into the 2 individual logarithms, log base a of your numerator, b, and log base a of your denominator, c, and they get subtracted now, unlike the last problem where when this was multiplication, they got added. Okay, so it's kind of the same thing, and you guys are old enough and smart enough now to understand that it's kind of a fine line between addition and subtraction and multiplication and division. So if there was a property where, oh, this is messy, wow, where multiplication led you to the addition of 2 logarithms, it's probably not too hard to believe that a division right here could lead you to the subtraction of 2 logarithms. And I really only have one example that I want to do with you guys right here, and that's the log base 4 of 1/64. Now, if you really know what's going on with your powers and you understand another concept, I don't want to say it just yet, you might be able to look at this and tell me the answer already. But if you can't, or if you're not 100% sure that your guess is correct, let's do this one according to the property that we just wrote down. We have a single logarithm, log base 4, of a quotient. So the property we just wrote says that we can break this down into 2 different logs and subtract them. Log base 4 of the numerator, which is 1, and then minus the log base 4 of the denominator, which is 64. And I do want to point out yet again, guys, we've got 3 different logarithms written here on this equation, but all of them have the exact same base. So you'll notice looking at the product property and also looking at the quotient property, the base of your logarithm never changes. Whatever it was to start with, that's what it is throughout. Now, hopefully, each of these 2 individual logarithms can be evaluated, and it's the first one that gives people trouble sometimes. The question here is, 4 raised to what power is equal to 1? Well, if you guys recall, any number raised to the 0 power is equal to 1, so that first logarithm just becomes a 0 there. And then minus, all right, and what's the second question? 4 raised to what power is going to get us 64? Well, let's run through the list here, guys. Obviously, 4 to the first is 4. 4 to the second is 16. 4 cubed, then, using your table if you needed to, 16 times 4 is 64. So we end up with a 0 minus 3, and our answer then becomes negative 3. Now, I said a moment ago that some of you might have been able to tell me the answer just by looking at this directly. Let's recall this fact right here on the bottom, guys, that if 4 cubed is 64, if we were then going to take 4 to the opposite power, negative 3, that would just be the reciprocal of this number right over here. 4 to the negative 3rd power is 1/64. So the original question in the first expression here, guys, was 4 raised to what power is equal to 1/64? And I can see that answer right here. It's 4 to the negative 3rd. So if you knew the answer to that right away, good for you, and you absolutely don't need to show this work right here. But there might very well be cases in the future then when that's not going to be as obvious to you guys, and this is a way that you can break it down and you can get that answer using this new quotient property. Okay, the third property we're going to talk about today is a really, really, really important one, so I put a little star by this. This is the one that really, really matters for what we're going to do next in section 7.1. 7.5. This is the power property for logarithms, and here's what it says. If you have a logarithm in some particular base here, base A, and if your product, and again I should have had parentheses here, if your product contains an exponent, if it's b to the c power, you can now take that exponent right here and bring it out in front as a coefficient of that logarithm. So that's why we have that written here as c multiplied by, and then it's the log base a of b. So really all that happened is we took that exponent and pulled it out in front of the logarithm. So that's the power property here, guys, and I'm going to show you how to use it directly, and then we'll kind of go a backdoor way there to see that it works. Again, it's not a proof, but hopefully it'll make you guys feel a little bit more confident in it. So what's going on in this problem? The log base 5 of 25 to the 7th power. Now, what I do not want you guys doing is trying to evaluate 25 to the 7th. I'm not even sure that your calculator is going to give you a nice number right there. Okay, it worked out not quite as crazy big as I thought. What is that, 6 billion, 103 million? Yeah, there you go. But now I got to wonder, 5 to what power is equal to that huge number? So there's probably a better way to handle it. When your product contains an exponent, the power property says, let's take that exponent and let's bring it out in front as a coefficient. So this now becomes 7 multiplied by the log base 5 of 25. And you don't have to write this, but effectively, I'm going to worry about that logarithm here first. And as I hope you guys can see, log base 5 of 25 is rational and pretty easy. 5 raised to what power is equal to 25? 2. And now we just end up with 7 times 2, and our answer here is 14. Now, my question a while ago was, even if you knew what 25 to the 7th was, there you go, does 5 raised to the 14th power get you the same result? And it does. And again, with calculators, this is a really easy problem to do, guys. Log base 5 of, and then what did we have there? 25 raised to the 7th power. So there's the answer. Modern calculators make this incredibly easy, but even as little as 10 years ago, this was a more complicated problem even if you had a calculator. Certainly 50 years ago, when calculators that did logarithms and did different bases didn't exist, this is a way that mathematicians had to go about this. But this property is incredibly important, guys, and I'll go ahead and give you just a little sneak peek as to why, because in the next section, we're going to be solving equations that might look something like this. How about something like 5 to the 2x minus 3 power is equal to, and I'm just going to make up an ugly number right here, like 78. I guess I didn't make up a number, but there you go. There's no logical way you would look at this and just figure out what the answer is. 78 is not a power of 5, so I can't just sit there and logically think of my way through the answer. But what we're going to learn in section 7.5 is that you can use that power property to take this exponent and bring it out in the coefficient if we had put a log right here. And of course, if you're going to do a log on the left, you would need to do a log on the right as well. So now, the way that's written, you could apply that power property we just talked about, and you end up with your variable now down on the base level as a coefficient of that logarithm, and it's much easier, that's the way you do it, it's much easier to solve the equation written that way. I don't want to get ahead of myself, but that's what that property is really useful for. Now, I'm going to go ahead and give you guys the change of base formula, but even more so than the 3 properties we've learned so far, this is a formula that's not really relevant anymore because of what your calculators will do that they wouldn't do in the past. So the change of base formula just allows you to evaluate a logarithm in any base with any product, the log base a of b. And what you'll notice here for the very first time, guys, is on the right-hand side, the base of these 2 logarithms is now different than it was just a second ago. In all 3 of the properties that we've done so far, the base of the logarithm has remained the same. But now, we're going to change the base of that logarithm from a, whatever it was, to c. And what I want you guys to notice, this is a way to read mathematics, guys, in a way that you're probably not very familiar with yet. There is no c in this expression here at all. That means that C can be something completely new and made up. It doesn't matter what you choose for the base of the logarithm, as long as you choose the same number here in both the numerator and the denominator. So the log base A of B can be broken up into the quotient right here of the log base C, where C can be any number you want, of B, which was the original product, divided by the log base C of A, where A was the original base. And guys, this formula was incredibly important until just a few years ago, because even a calculator as relatively advanced as the TI-84 that you guys are using now really only did logarithms in two bases. Your calculator on the left-hand side right next to the 7, guys, has a button that just says log on it. And if you hit that button, all your calculator is going to write is log. And remember, there is no base after that. Well, I don't know what I was drawing there. Remember, guys, that if you have just a log with no base, that's that's terrible looking. That is log base 10. So that's what we would call the common log, and your calculator would do that back in the day. The other button that your calculator has right below the log button, it's right next to the 4, here you go, is LN. That's the natural log button. So when you hit that, your calculator just displays ln, but what that really means, guys, and I hope you remember this from 7.3, is log base E. So for about the last 30, probably about the last 30, maybe 35 years, your calculator was programmed to do logs in base 10 and logs in base E, and that was it. It was not equipped to handle logs in base 6. So let's go ahead and jump 25 years in the past, okay, and talk about how we would have done this problem back in the 90s when everybody was listening to grunge and wearing flannel. All right, guys, we would now make this log base 6 of 100. We would make this a log of whatever number base we wanted to do, and probably log base 10 was the easiest way to do it. So make up whatever log base you want, but it really only makes sense to choose base 10 or base E, because that was all your calculator did. Now, this B value right here is the same product in the numerator, so this is now log base 10 of 100. Down on the bottom, it's another logarithm with the same base here as the one we chose up above. So that would need to be log base 10 again, and this product is now A, which was the base of the original logarithm, and that's going to be 6. Now, let's see if this one actually works out. The change of base formula works this way, and I'm hoping you guys recognize the numerator is actually rational. Log base 10 of 100 is 2, but the denominator is irrational. Log base 10 of 6 is some god-awful ugly decimal number, so since we're going to have to divide anyway, I'm just going to go to my calculator here, and unfortunately, guys, I'm not able to show you this exactly the way it would show up on yours, but here's what I would do if I were you guys. I'd probably hit alpha and then the X button right next to it to get a stacked fraction. And you guys would hit your log button. Now, when you hit your log button, you don't get the opportunity for a base like I did, but I'll go ahead and type it in. You guys are going to skip that 10 and just type in log 100. So just kind of ignore the 10 there, guys. And then when I go into my denominator, you should do the same with me now. Let's hit this log button again. And again, you'll ignore the 10 right here, but there you go. And we'll type log of 6. And when we hit enter now, hopefully we all get the same decimal value of 2 point blah, blah, blah. You got to read your directions carefully here, everybody. Very often with these logarithm problems, they actually want you to round farther than we normally do. I'm going to go to 4 decimal places, 2.5702. So let me write that one down, 2.5702. Now I think that's my answer. If it were, that would mean that this number here, 6, raised to this power, the 2.5702 power, should get us a value here of 100. Well, what do I know, guys? I know that 6 squared is 36. And I know that 6 cubed is 36 times 6, which is 216. So if there is 6 to a power here that equals 100, which obviously is between 36 and 216, I feel like this power should be somewhere between 2 and 3. And this number is, so I already feel fairly confident about this. Let's try it real quick though, guys. And the best way to do this, you can do this with me on your calculator, is take 6, hit the caret key, and now rather than manually typing in 2.5702, you guys should just be hitting second and then the negative key, which says ANS, which means last answer. And if we do that, yep, I got exactly 100. What would have happened if I typed it in manually? 2.5702 for my power. I bet I'm going to get something very close to 100, but not exactly right. Yeah, okay. So probably close enough to make me feel good about my answer, even if this is what I got, but it's both faster and more accurate to hit second answer. So that is always a habit that I want you guys to use and to try to get into as we're doing this. All right. That's the change of base formula. We're not going to spend too much more time on it than that. The last two things we're going to do in this section of notes, guys, are kind of talking about how to use these properties to do two different things, although it's really two ends of the same coin. The first thing we're going to do, and you will see this a lot on your homework, and I'm sure you'll see it on the test for Chapter 7 as well, is to expand a logarithm. So I took a second just to write down what that means. Expand means to take something small and make it bigger. So in parentheses, I wrote that expand means to write this logarithm, which, by the way, you'll notice right now is just a single log. There's just one logarithm here. But we're going to try to write this log as multiple logarithms, but each one of those logarithms needs to be very, very simple, of the form log base A of b. So that b is just one single number right there, nothing too complicated. So what's going on in this problem, guys? We've got a single logarithm, log base 2, but of a fraction, 5x over y cubed. So this right here is too complicated here because we said that b has to be just one simple number. So the very first thing I think we're going to do, let me slide this over a little bit. The very first thing we're going to do is recognize that we're taking the logarithm of a quotient. So we're going to use the quotient property and make this the log base 2 of your numerator, which is 5x, I'll put parentheses around that, minus the log of the same base of your denominator, which is y cubed. So we just used the quotient property there in order to do that. Now, we've made progress right here. We've broken one logarithm down into two, but remember, b needs to be a single number. That's not a single number, and neither is that. So what are we going to do with each one of these? Well, this first logarithm right here is the logarithm of a product, 5 times x. So we'll use the product property and make that the log base 2 of the first factor, which is 5, plus the log base 2 of the second factor, which is x. And right now, guys, I like what I see, because what we were looking for here was log base A of b, just a single number there by itself. 5 is a single number, so that one's good. X is a single number, so that one's good. All right, let's keep moving along now. Minus. Now, what made y cubed a little too complicated is the presence of that exponent right there, which is 3. So now we're going to use the power property and bring that 3 out in front of the logarithm and make it a coefficient. 3 times the log base 2 of y. And now we have a logarithm there just of a single number as well. So the fact that we have 3 logarithms here, but each one of them has a product that is just one single number, tells us that we are done with this problem here, guys. And that's what it would look like to expand this one complicated logarithm into, it turned out to be 3 very simple logarithms. But with addition, where there used to be multiplication, subtraction, where there used to be division, and a coefficient where there used to be an exponent. All right, so that's what this problem would look like here, and that's our answer for problem number 5. Now, problem number 6 is going to ask us to do the same thing, but in the opposite direction. So the opposite of the word expand is to condense. All right, and condense means to take this big messy expression that we have here with multiple logarithms and write it just as one logarithm, even though that logarithm is going to be very, very complex in all likelihood. So what I want you guys to realize right now is that this problem, the way it's presented to you right here, kind of looks a lot like the answer to this problem here. This one is multiple logs added or subtracted or anything like that, and it began life as one single logarithm. We're going the opposite direction here. We've got 3 different logs, and we eventually want this down to just one logarithm. So let's see what that one would look like. You kind of have to work your way from inside out, guys. The first thing I see inside the brackets, log base 8 of 3, you can't really do anything with that. But 5 times the log base 8 of a, I'm eventually, on the next step, going to put these 2 logarithms together. But what's in the way right now? This 5 needs to move. So we're going to reverse the power property, everybody, and take that 5 there and make it an exponent on the a. So this is going to become the log base 8 of 7. There's nothing I can do with that now, plus a 1/2. And in brackets, can't do anything with the log base 8 of 3, but I'm now going to make this the log base 8 of a raised to the 5th power. And now we've got 2 logarithms in the same base with no coefficients. That's important, everybody. So we're going to combine these 2 into a single logarithm using the product property. So everything else just tags along. Log base 8 of 7 plus a 1/2, but now in brackets, this is going to be the log base 8 of the product here of 3 times a to the 5th, which is going to be just 3 a to the 5th. There's nothing else we can do with all of that. Okay? All right, so that's where we are right now. Let's keep making progress here, guys. The next thing that I think is in our way is the 1/2 right there. Now, I wrote brackets there around the log base 8 of 3a to the 5th, but they really don't need to be there because that's just a monomial inside. So this is 1/2 times log base 8 of 3a to the 5th. And just like we got rid of this coefficient here by reversing the power rule, we're going to do the exact same thing here. That 1/2 is going to go right there. So where are we now? The log base 8 of 7 plus, this is now going to be the log base 8 of, now guys, hang on for just a second, we could write this as 3a to the 5th to the 1/2 power. That would not be wrong, but what I want to remind everybody, something we learned a while ago, a 1/2 power is the same as a square root. So I think this would be a little bit cleaner if we wrote this as the log base 8 of the square root of 3a to the 5th. I like that a little bit better. And now, guys, we are just about done with this one right here. Oop, oop, oop. Give myself a little more room there. Okay, gotcha. Just about done with this one. We've got a log base 8 of 7 on the left, plus a log base 8 of that square root on the right. We can now use the product property and put those 2 together into a single logarithm now. The log base 8 of the product of 7 times the square root of 3a to the 5th. 7 times the square root of 3a to the 5th. And there is nothing else we can do to clean that expression up, guys, so that is our answer to this last problem here. So that's what it looks like to condense a logarithm. You start off with a long expression that, yeah, has multiple logs, but each one of those products is very, very simple, and we condensed it. Definitely wrote it in a more efficient way, but it's a little more complicated. It's a single logarithm, but the product then involves a lot of things: multiplication, square roots, multiplication, and exponents. So those last 2 problems, 5 and 6, is what you're going to see a lot of there, guys, in order for you to be able to expand and condense logarithms right there. So that's kind of how these problems are going to work out, and you're going to see a lot of those on your homework here on 7.4 and on your test on Chapter 7. So let's keep those properties handy in your notes as you're going through those, and good luck on the homework, everybody.